Good evening, all. Welcome to the week 10 session on Optimization Fundamentals course. This week, we will be discussing on the following topics on the introduction of different optimization methods, how do we define the rate or order of convergence, and then we will discuss linear search, followed by steepest gradient descent, Newton's method, and finally, we will discuss on penalty method for a constraint optimization problems. The first three that are discussed here, the linear search, steepest gradient, and all these methods are for unconstrained problems, and then we'll extend this particular method for constraint optimization, so you can use the same methods even in constraint problems. So what exactly are we trying to do is, we started out with saying that we need to find an optimal for this particular problem, minimize f of x for some x. This is an unconstrained problem. There is no restriction on x, so x belongs to Rn, and we're assuming that the function is continuous and differentiable up to at least first order derivatives. Now we already know that in this kind of scenario, we have the solution will belong to this particular set where the gradient is equals to 0 and the Laplacian will be positive. Like the x will belong to this particular, the solution will belong to this particular set is something that we already know. But the problem now is, how do we find the values of x in this particular set? We cannot search through all the possible values of x and see at every point whether this gradient is, like, instead of searching through all the points where f is like, search through all the points and remember what the values of f are and then find the minimum of them. We kind of reduce that from there to here, where you only find the gradient and Laplacian and check whether these conditions are satisfied. If these are satisfied, then in those points we will find the minimum value. Now, even for this, we have to go through all the x values. So we have to come up with a strategy of how to search all the x values and eventually come to a solution. And that is exactly what this optimization method is about. How do we find or formulate a strategy, and what information can we use so that we can reduce the number of values of x that we are searching for. So that is the whole point of these optimization methods. And as in any method, there could be several different strategies. Each one can propose a different strategies. How do we know which strategy is better or something? So we need some way to kind of evaluate these strategies, and one way is called the rate of convergence or the order of convergence. So we have a sequence Rk, like we start with some iterate x and then we keep improving changing the values of x eventually till we reach a particular solution. So we define this R, this R can be one of your solutions. So this sequence will converge to some particular value R star. Then we define the order of convergence by this beta, where the limit as k tends to infinity, as you keep on iterating, Rk plus 1 minus R star by Rk minus R star to the power beta should be some finite value. Or, like, put simply, this particular thing becomes constant, the constant over here. So Rk plus 1 minus R star should be is, as k tends to infinite, this will be equal to constant times Rk minus R star power beta, where this beta is my rate of convergence or order of convergence. So how do we calculate this beta? So we generate the sequence till we reach R star, and then once we have R star, we can find this value and see, like, you have to just take you can plot it, or you can directly take the logarithm on both sides. So ln Rk plus 1 minus R star is non-constant. So from this, you know the values of Rk plus 1 R star and these values. So from there, you can estimate the value of beta if you draw this as a plot. If you draw this plot, then it will be something like this. This will be my ln C, and the slope will be the beta, and this is my order of convergence. And depending on the value of beta, we have different names for it. If beta is 1, we call it a linear convergence. Beta is 2, we call it quadratic convergence. If beta is 1 and this particular constant equal to 0, so that the limit is actually going to 0, then we call that a superlinear convergence. There are just names for different values of beta. But maybe I should ask a question here. So if you have like, To calculate beta, we need to know both the values of rk plus 1 and r star. But when we are solving an optimization problem, we only know this rk plus 1. We do not know r star beforehand. Like only after finding the solution, we can use this particular definition to calculate the value of beta. So if you devise a new algorithm, so how do we find it? Most realistic, like practically what we do is instead of doing with r star, we'll do something like this. So we take the current iterate and the previous iterate. This is something very similar. Even in CFD, you would be doing something similar like this, or in any of the optimization algorithm. Since we do not know the final value, because if we know the final value, we'll directly use it. We don't even care about the rate of convergence and all this stuff. So we just take how much the iterate value is changing as the iterations are proceeding. So this is what matters. So this is what we try to find out. So essentially in the plot, instead of r star, you'll replace it with the previous iterate. In the first one, it will be rk. In here, it will be rk minus 1. Here, it will be rk. I hope this is clear. Now, let's say if for example, let's say if beta equals to 2 is quadratic convergence. So if it is a quadratic convergence, does it mean it is also linear? Because if you see the definition over here, the definition doesn't say like there is an extra term here, the supremum of beta, such that this particular thing is satisfied. So there could be multiple values of beta. Like if I just keep this definition, there could be multiple values of beta. Out of all those values of beta, I'm just taking the maximum value, supremum of them, and that is what I'm defining my rate of convergence as. So if a particular algorithm is converging quadratically, then it means it will also linear is also included in it. So if you think of this, so this particular value rk minus r star as k tends to infinity will eventually, because at k equals to infinity, this rk will be equal to r star. So this particular quantity is always less than 1 for large k. If this quantity is less than 1, then any power of it, say r square or some beta, will also be less than 1 if beta is some positive quantity, as we define here. So what am I trying to say here is, if you just understand like this is my 1 and this is my rk minus r star, this is rk minus r star square. All these values will be less than that, so you'll have rk minus r star cube and so on. All these values will be less than this particular quantity, and what we are defining now is if this particular beta ranges in this. So if your rk plus 1 by this particular quantity is in this region, then beta will be 1. So we are calling this particular region linear, this particular region we call quadratic, and so on. And if this is satisfied, for example, if rk plus 1 by rk minus, sorry, not this one. So if anything in this is what we are calling quadratic, and anything in this is what we are calling linear. So if linear is a kind of subset of what quadratic is. So if quadratic is kind of satisfied, then linear will also be satisfied. But we are just taking beta equals to 2. Like this plus this, we are calling it as quadratic convergence. I hope this is clear. Now we discuss some algorithms. The first one is the line search method. Line search is a very simple one. So you start with some iterate xk, x naught, and then you keep iterating such that xk plus 1 is xk plus some alpha k times pk. So this is my step delta x. And delta x is chosen such that you take alpha is basically some confidence that you are giving on the particular direction. So you start from a point and then you keep moving with some alpha times pk. So this is my xk. You take some particular step and then you will move to the new point xk plus 1. So the questions now are how to choose pk and how to choose alpha k. Depending on these choice, you have different methods. So what is the choice for alpha? The first one we'll start with alpha. So how do I choose my alpha? Again, even in alpha selection, we start with some alpha value and then we will see whether some conditions are satisfied. The basis for choosing these conditions is whenever we are moving, we know that pk is basically the direction in which the function value is decreasing. So if f is my function, del f is the direction in which the function will increase. So we will always choose the direction that is parallel to minus del f, because if I go in this direction, then f will decrease. That is what we are writing, like pk will be proportional to minus del f of xk, so that the function value will always decrease. But now the question now is how far should I go? Say for example, you have something like, say this is my f of x and this is my x. So you have a function like this, and say you are at some point here. So let's say this is my xk. The question now is how far should I go? Where should be my xk plus 1? It can be here, it can be here, it can be here, it can be anywhere. But which point to choose is some pk will only tell me that I have to go in the direction of decreasing gradient. So the gradient is in this way. So it only tells me that I have to go in this direction. At this particular point, I have to go in, like instead of going towards the left, I should be going towards the right. That's all the information I have from the gradient pk. But now the question is how far should I go? That is what the alpha will decide now. So the idea is the first step, the first condition here tells you that go till the value of the objective function is not increasing beyond what the current value is. So if you start from here, any xk plus 1 that you choose beyond this point, after this f is continuously increasing. So all these points, whatever are lying to this side, are not useful, because any of those points f will be higher than what I already have. So I should not be taking any points in that region. So that is one limitation I'm getting from the first condition. So it basically tells you that your objective value should not be greater than what the current value is. But then it's not exactly equal to objective value, but then we are saying up to some tolerance. C1 is something that we specify, that okay, why should I go this far? I can stop even before. I can say something like this. So you include more reasons saying that it has to decrease by a certain amount. Like instead of saying that the new value can be any value between the current value and anything lesser, we will say that it has to be strictly lesser than this. So by some quantity, C1 times this thing, if you remember this, pk is proportional to minus del fk. So multiplied, both of these multiplied, when you do the scalar product, it will be some negative quantity. So it will be less than f of xk. So we say that you have to be less than, instead of saying it to be exactly equal to this, we will say it has to be less than certain quantity. So this is what the first condition says. So let's say this is W1. So you have to choose, you have to pick a value of alpha such that the new xk plus 1 should give me the function value which is lower than the current value by a certain amount. How much should I take, that is again depends on the problem and all that stuff, but that is something that we have to specify by the, depending on the problem, we have to do trial and error and stuff, and that all that information by varying this particular C1. Secondly, even in scenarios like this, even if you fix like this, what is happening is my minima is somewhere here, but then I am trying to search in all this extra space. All this extra space from all this extra space is something that I should not be wasting searching, because I know that there is no minimum in that. So in order to enforce that condition, what we try to do now is we put in another constraint saying that whichever direction you move, the new point that you are going to get, at the new point, the slope should be this particular value. Again, at the new point, the slope should still remain working, like I've seen. So if you start moving from this point, you'll keep going in this direction, because at every point your gradient is still pointing downwards, so you'll still move towards right. So my the pk direction is still remaining the same. But the moment I cross this minimum point, say for example I'm at this particular point, the gradient will be pointing in this direction, which means my pk will be pointing in the opposite direction. So it will give me an indication that I have to move back. So what we try to do is you take a step such that you don't have to come back again. That is what the second criteria tells. So how big you have to take a step is dependent on how big you are. The step should not be too big so that you have to come back and forth. That is what the second condition states. You take a step so that the gradient that you are going to get at the new point still points in the same direction. That is, you do not go into this region. So this region is eliminated and this region is eliminated. So eventually you'll be fixed only in this particular region. Now again, what alpha to choose even in this particular region, again it changes. So depending on what the value of C2 is, you can end up here, you can end up here, anywhere on this particular thing, and that will decide what the region you have to, which region your alpha will eventually end. So what we do is we start with some alpha and then we keep decreasing the alpha value. So we start with a very big alpha and then we keep decreasing till both these conditions are satisfied. And once both these conditions are satisfied, we use that particular alpha. We already know the pk value and then we'll update xk plus 1 and we'll keep doing this till xk plus 1 converges to x star. So this is basic idea in line search. This is clear? Yeah. So next one is the steepest gradient descent. So here we have just told that pk should be proportional to this, but we didn't say what exactly the value of pk should be taking. So that is where the steepest gradient descent comes. So in this we explicitly say that pk is exactly equal to the gradient of f. So that is why we are calling it the steepest gradient descent, because you are always taking the maximum steps. But eventually the problem would be that if you keep taking this bigger steps, you might actually keep going that back and forth thing. The next one is exact line search. So we know what the pk value is. All this particular method tells you is you have to take the direction such that it is equals to minus the gradient of f. But then what is the value of alpha that I have to choose? So this is only for a specific case when you have a quadratic problem of this particular kind where f is something like this x square and some x term. So this is a quadratic equation. In this particular scenario, I can directly calculate analytically calculate LF, so that which will give me qx minus t, and from there I can directly calculate my x star. So this is my optimal value. So it's like a single step thing. So if, for example, to solve this particular problem, if I want to use the line search method with steepest gradient, say for example, then all we have to do is we know pk. This is the from steepest gradient descent. We know that pk is this. But now, how do I find alpha k? In exact line search, only for this exact line search, whenever we say exact line search, what we are trying to do is with this particular alpha, we will calculate f, and then we'll take the derivative of f with respect to alpha and equate it to 0. That will, if I once I equate it to 0, I'll get a particular value of alpha, use this alpha and keep it inside this particular equation. So I'll get my xk plus 1. So the difference from this and the previous algorithm I have shown is how the way that we define alpha. So previously what we told is you satisfy just these two conditions, any of these conditions, either first or the second condition, and the alpha is not in any way optimal or something. But now we are kind of putting an extra constraint that the alpha that you choose should also give you an optimal value of f at the next step. So when I use steepest gradient descent with this, for this particular problem, it will be quadratic, it will converge quadratically, but in general, this will be linear. It will have a linear order convergence. So how did I get this alpha? It's basically, you can directly get it from here. So if I take del alpha k of f of xk plus 1, so if you apply the chain rule, so this will be del with respect to x, f of xk plus 1, and then you will have dxk plus 1 by d alpha. This will give you del xk plus 1 by del alpha will give me pk. You can quickly do this calculation. So this will be q times Let's just take the other one. Be qxk minus p plus q alpha k pk times pk transpose. So qxk minus p is basically my del f. Pk is minus grad f times this quantity. I think that it's something wrong with the transpose thing, but I think you got the equation. So this will indirectly give you this particular relation. From this you can solve and get this. I think I missed out the transpose somewhere. Yeah, but I think you got the crux of it. So this will give you what the value of alpha is. But again, the problem now is here we have a very simple problem. We know that f of x is quadratic in nature. So it is actually quite easy to solve this particular derivative and then eventually come with alpha. But imagine a complex problem where you do not know f of x directly. Say, for example, if you are doing some CFT simulation and say the objective function is something like you need to find the heat transfer function or something, the heat transfer coefficient or something. Then what would happen is your input will be, say, for example, if you calculate the heat transfer coefficient with your different boundary conditions, whatever boundary conditions you have, and whatever inlet condition, let's say all the boundary conditions, then you want to maximize the heat transfer coefficient or something like that. If that is a problem you want to solve, then this particular equation that you're going to have is something that is very complex, and you cannot directly get the value of alpha always. So it's like only for simple problems or kind of analytical ones where you can solve for alpha is where this particular exact line search can be used, but in general you cannot directly use this technique. The next one is the Newton's method. So the gradient descent will give me linear convergence. Then comes the Newton method. In this, what we try to do is, in addition to using the gradient value, we also use the Hessian value. So what we do is, previously we have taken pk to be equal to minus del fk, but now we are also saying that we are adding this extra term, which will ensure that both the effect of the gradient as well as the second order derivative of it, so that you not only take into account the current value of f, you'll also take what is the value of gradient. So for example, if you are at a particular point, what we are doing is we are checking whether the gradient is increasing in this direction or this direction, and whichever is the decreasing one, we'll keep moving this direction. But then now what we are trying to do is, in addition to this, we are also checking whether the second order derivative is kind of giving me in the right direction. So for example, if I have a function like this, maybe let's take an oscillatory function. Let's take a quadratic function. Just take a quadratic function. If you start here in the steepest gradient descent, what you will do is take the gradient and then you keep going here, and then you keep going here, and then this is what you will keep doing with steepest gradient descent. At every point you will take the gradient. Okay, it should have been tangent. I should have drawn it. So if you start at a point, you take the tangent of it, and you'll end up at some other point, and then from there you take a tangent, you'll end up somewhere else, and from there you keep bouncing back and forth to eventually reach here. But in order to prevent this, what we can do is, instead of going directly jumping too far, we will also take into account what is the value of the second gradient Hessian there, and we will kind of do the calculation beforehand itself and say like, why should I go this far? Instead, we will only stop somewhere here, so that the rate at which you converge will be much faster than doing it directly. But the problem again here is, to calculate this Hessian itself might be difficult depending on the objective function that you have. If you know the analytical equation of the function like this, then you can pre-calculate the value of gradient, Hessian and all that stuff, and you can directly incorporate it. But most often we do not have the objective function in analytical form. So we need to come up with a different way to calculate this Hessian. So what is something that we possibly do is, you calculate f, you store say f0 at current iterate, f1, f2 and all these iterates, and then you perturb it and then calculate say f1 minus f0 by whatever the perturbed quantity you have, and from this you'll also calculate f2 minus f1 by delta, and use these both equations to calculate my second order derivative, approximate this one. So this is my bk. So if you do not have access to the analytical value of analytical function, then you have to do something like this. You have to use some kind of finite difference to calculate these derivatives, and then from there update your step value. If once we do things like that, then it doesn't behave like a quadratic problem. Then the convergence will actually reduce. And also, the quadratic convergence of this particular method is only in the neighborhood of the optimum. So only if I'm close to the final solution, then it will converge quadratically. So if you consider the previous problem, like if you have something like this and this is my minima, only in some neighborhood around this particular point is where we have quadratic convergence. If I'm very far from it, again the bouncing will start. So you might end up here, different places, and it won't be actually be quadratic in nature. It might take a very long time to converge. So in this particular method, the choice of your initial value plays a very critical role. So if you choose a initial guess very far from it, then this method might not even converge sometimes. You might actually end up going somewhere else instead of to the final solution. So what we usually do is we combine, like we use a hybrid kind of thing. So when you are far off from the optimal region, so initially you start off with some other optimizations method, which we have not discussed as of now, but there are other methods which can, some search methods like the line search or gradient descent or some other method we will use initially. And then we will monitor how the value of, how the iterates are changing. So we'll monitor this. Once we know that this particular quantity is kind of, say if you plot this particular quantity, ideally, eventually it has to go to some constant. So initially it might be very high, and then eventually it will kind of asymptotically reach some small value. So like once you notice that these values are kind of reaching some stagnation, then you switch your method to Newton method. Then you can converge rapidly. For say, for example, somewhere here, you switch to Newton method, then it will converge very rapidly. So you combine a search method like the line search or something initially, do initially that, and then kind of identify the region where you are close to optimal. Once you know that you are close to optimal or something like that, like something like this kind of asymptotic thing is reaching, then you switch over to Newton method. Then you can have faster convergence. And all these methods are again assuming that you have an unconstrained problem. The moment we have a constrained problem, the problem is something like this. Previously we have x belongs to Rn, but now there is two things that I have to do. I have to ensure that this x is not is always belonging to the set yes, and also ensure that the value of function is decreasing. So one straightforward way is something called a barrier method, where what you do is you keep iterating the values of x, and then you check whether the x is within the feasible region or not, and if it is exceeding the feasible region, then you bring that point onto the feasible region. So for example, if this is my feasible region, initially I start over with this, say this is my x0, then I know the gradient, say I'm using line search method, then somehow I ended up at x1, say something like this, and from there I went to x2, and from say here I went to x3. But when I check that x3 is it's not in the feasible region, so what I do is I'll map this point back to the nearest boundary point, whatever I have. So this will be my x3. This stays say x3. And from x3 again, I'll have to move in some direction. So either along the gradient or depending on whatever the gradient direction is, I'll ensure that these points, the iterates that I'm getting are not going outside the domain. That could be one way. The other way is something called a penalty method. So what we do here is we take the original function and then we convert this constraint problem again to an unconstrained problem with an extra function. This is similar to your Lagrange multiplier thing that we discussed before, where we converted the problem from a constraint to an unconstrained optimization. So we just add a penalty function. This penalty function will ensure that this constant will decide that when you try to minimize this new function, if this constant is too high, then eventually the algorithm will try to make this particular quantity to equal to 0. And this quantity will have your equality and inequality constraints. So in my equality constraint, I have p of x equal to norm of h of x or square or something of this sort. So if this h of x is not equal to 0, this will be some finite quantity. And if this c is very high, then the only way to minimize this entire function is to make this particular p of x equal to 0, which means making this h of x equal to 0. Similarly, for inequality constraints, we try to minimize this particular quantity. So we know that g of x should be less than or equal to 0. So whenever this is less than or equal to 0, that particular penalty will be 0 because it shouldn't affect my optimization problem. And whenever this is some positive quantity, then that particular quantity enters the P of x. So if I try to minimize Q, then it will try in a way to make to minimize P as well as F, but it will eventually find that P where G of x will become negative, then this particular quantity will become 0, and the problem will be equivalent to saying minimizing F of x. So this is a kind of an indirect way to do the same thing. So whenever you kind of move away from the feasible region, both these terms will add up to my penalty term, and that will drive my optimization algorithm to minimize P. Eventually, that P will be 0 when h of x equal to 0 and this g of x is less than 0. Then it will be equivalent to solving the original problem. But obviously there are challenges with this, like how do I choose the value of C? You start with some value, you keep increasing the value of C, and you see how your optimal value changes. So eventually, it's ideally what we expect it is, as k tends to infinity, as this particular constant tends to infinity, then the solution will match. But we will see in the next week lectures that you don't have to really go to infinity, because that is not practically possible. You can't keep trying all these values of C. Maybe solving one optimization itself might be computationally too expensive. Now solving 100 different optimization problems and then tabulating all of them will be even more difficult. So how do we solve this problem is something we'll discuss in the next week. Yeah. So are there any questions up until here? Yeah. So say for example, if you consider this is my domain, I am at some point xk. What line search tells you is I have to move to x1. How far should I go? This is the whole point in the line search thing. So you keep moving in the how do I fix this delta x? So the like Newton method is also kind of a line search, but then the way that it is different is how do I choose this delta x? In exact line search, we are doing in one way, where the direction, like here you have two components, you have to decide how much the step you have to take and the direction you have to go. In Newton method, we are kind of fixing this particular quantity to be this particular thing, where you are considering both the Hessian as well as the gradient into account. But in the normal line search, we are just taking these two conditions. Like you just ensure that your f is decreased, it's sufficient. As long as you are going in a direction where f is decreasing, that is fine for me. We are not using the second order information, like how the Hessian is actually changing also. If you want to visualize it or something, then I think in the lecture video there is a visualization where he shows how this actually moves in the objective plane. You recollect? So even this Newton method is kind of a subset of your line search, right? Line search is kind of the broader thing. Depending on the value of this step is where the different methods come. If one kind of, if I just choose pk equal to minus del k, then it will be steepest gradient descent. If I choose this pk to be this particular thing, then it is Newton method. I think I didn't get your question. Mhm. Okay. Okay. I think I understood your question. So, okay, first of all, there are no constraints in it. In any of these techniques, there are no constraints. All of them are unconstrained. So what we are trying to do is, if you imagine the x is this is your domain of x. So all we are doing there is we are at a particular point and we are trying to move to a new point. There are different points on this particular line. All we are doing is searching on this line and finding a new point xk plus 1. That is what we are trying to do there. Not an optimal point, but it is some point that will satisfy certain criteria. Like if at this particular point there is some f value, if at x plus 1 there is some g value, I need to ensure that g is less than f and the gradient of g so and so and all those conditions. The main solution is available on this line only, right? Because this line is basically the set of all x's that are possible. X belongs to Rn. If you have a 1D problem where f of x is x square or something, then this is where solution lies. All I have to do is search along this line and find the solution. But I should not be searching over all the infinite points. I have to restrict to some possible some small subset and get my solution faster. It's not a completely different kind of thing. The only way is how do we choose delta x. So only for quadratic functions or some functions where you can leverage the second order information. So for example, if I know that function is like this and I'm at a particular point, then the gradient will give me that you have to go so and so. So let's take one step and then draw it, then it might be clear. So let's take a simple function. Say you have f of x equal to x square. So this is my function. So let's say I start from the point, this is say x equal to 1. This is my initial case. So now what we are trying to do is we have to find x1, like we have to find the next point. So I am here, I want to go to the next iterate. So all this says is x1 is x0 plus some alpha times pk. This is what my line search tells. So what is my alpha and p? So let's say what is my p? P should be minus grad f. Let's say we are doing steepest gradient descent. So that will be minus del f. So that will be minus 2x at x equal to 1. So this will be minus 2. And now I have to choose an alpha. Let's say we start with say alpha equal to some 0.01 or something. Then x1 will be x0 minus so this will give me some 0.98 or something. So from 1 I have moved only up until here. Both my Wolf conditions are satisfied. The function value decrease and the gradient is also kind of decreased now. So this is what the first thing will tell you. This is what a simple line search will give you, steepest gradient descent. But now let's say if I want to go with the what you say, the Newton method. So then what do I do is I'll also calculate del square f. What is my del square f? 2. So this will tell me the step in Newton's method. So like this is steepest gradient descent and this is Newton method. So P will be minus del square f inverse times del f. So if you calculate this, so this will be minus 1 by 2 times the gradient is 2. So this will be minus 1. So if my P is minus 1, what is my x1? Is x0 plus P. X0 is 1 minus 1 equals to 0. So you started here. So this is what my gradient descent is giving. But once I do Newton method, I'm directly coming here. Because we are using this additional information about the Hessian, it knows that, okay, if I'm here, and instead of if I stop here, even here, if you see the gradient and if you see the gradient here, at both these places, the gradient is still negative, which means I can still take a bigger step. And how big I can go? I can keep going till I reach this particular point where the gradient is equal to 0. Because beyond this point, your gradient will keep increasing. So if I go in that direction, then my objective value will keep increasing. This is kind of ensures that you take the optimal step. This is only for a quadratic function. If you take, for example, f of x equal to x cube, let's say you take f of x equal to x cube and you are at the same point. Then if you calculate Newton method, the del square f will be 6 and my p will be minus 1 by 6 times grade f. This will be minus 1 by 2. So x1 is x0 plus this equals to 1 by 2. So from 1 you are only going to 1 by 2, and then if you do another iteration, then you will from there you'll eventually you will converge eventually to 0, but then in single step you won't be reaching it. But now if you do the steepest gradient descent here, your grad f will be 3. So P will be minus 3. So x1 is going to be 1 minus say 0.01 times 3. So you can see this is 0.5 or something, this is 0.97. Your solution is 0. So this is converging faster than this one. Just because you know that you are using this extra information to choose the value of alpha. Hessian is basically your curvature. This, so if you calculate the Hessian any of these points, it basically tells you how curved it is. So if you have a straight line, Hessian will be 0. If you have this any of these straight lines, it will be 0, right? If you have a straight line, the slope is your gradient and the gradient of that is 0. So if you have, what a Hessian tells you is how curved that particular thing is at that particular point. Okay. Okay, then we'll quickly solve some problems. So you have an unconstrained optimization problem where you have to maximize f of x, and your variable is x. Assume f is differentiable. The line search algorithm is again the same. Xk plus 1 is xk plus alpha k times pk. What is a suitable choice for pk? Which of these is true for this particular case? Can I take this particular thing? The only difference from this and the one that we discussed some time back is here we are trying to do a maximization problem. The previous one is a minimization problem. So when we are trying to maximize a function, we have to move in a direction in which the function value increases. So I have to move in a direction in which the gradient is positive. So this pk should be in this particular direction. If I go in this is for a minimization problem. This will maximize the value of f because along the gradient direction f will increase. So what about this? Can I go in this direction? This doesn't tell me anything. This only tells me the curvature. It doesn't say whether the function will increase or decrease or any of that sort. All of the information is there in the gradient, not in the Hessian, so I cannot use this. I cannot directly take the x value as well. So yeah. Again, second problem. Consider an unconstrained minimization problem. Let pk be a descent direction. Any steps as alpha that satisfies the strong Wolff conditions also satisfies the weak Wolff conditions with the same constant c2. Is true or false? So what is my the constraint is something like this. If you collect it is gradient of f, something like this, should be greater than or equal to c2 times the gradient should be greater than this. That is your weak constraint. This is my weak constraint. And what is a strong constraint? The strong constraint is the absolute value of this. So you take, I'm just writing like this, times pk should be less than or equal to c2 times. This is the weak form and this is the strong one. So now the question says that if a particular pk satisfies, if a particular step size alpha, which is says alpha, so let's just put alpha here. If a particular step size alpha satisfies the strong Wolff condition, so if this is my A and this is my B, so if A is satisfied, does it imply the B will also be satisfied with the same value of C2? Is this true or false? So yeah, So if this particular thing is satisfied, we know that pk is something like minus grad fk. So transpose this is going to be some positive quantity. So this particular thing is a negative quantity and this is a negative quantity. So when you take mod of them, it will be positive. So like this negative quantity times this. So whenever this particular quantity is negative, then this mod will be replaced with a negative sign. So because of the negative, the signs get interchanged. So essentially this condition will boil down to this condition. If pk is minus del fk, so then you have both the conditions to be same. So C2 will be the same. Okay, now we have a quadratic function that we want to minimize. F of x is half x transpose x, for some x belongs to Rn. It's an unconstrained problem. Then starting from an arbitrary initial point, we arrive at the optimal solution in only one iteration using the steepest descent method with exact line search. Is this true or false? Okay, so how do you say it is false? But then here I am saying that we are using steepest descent with exact line search. What do we do in exact line search? So the method is something like your next iterate is xk plus some alpha k times your pk, and I'm saying we are using steepest descent. So pk will be minus gradient of f of x. So let's take it simple. Instead of considering it Rn, let's say x belongs to R, and your f of x is x square. This is what we solved just some time back. So your p will be minus 2x, and then xk plus 1 will be xk. I'm just writing alpha k to be alpha times xk. So this is what I have as xk plus 1. And what we do in exact line search, like previously what we did is we just took alpha to be some particular value that satisfies the both conditions. That is the normal line search. But in exact line search, what we try to do is we try to make the gradient of f of xk plus 1 with respect to alpha to be equal to 0. Like we find an alpha that will minimize this particular value of f. So at each and every step in your line search, we are again doing another optimization problem now. So this del alpha will be what? So this will be dd alpha of f of xk plus 1. So that is 1 minus 2 alpha xk whole square by 2. And this will give me something like 2 into 1 minus 2 alpha times minus 2, 0. So this will give me alpha as half. So if alpha is half, then xk plus 1 equals to 0. So in one iteration, I came to the optimal solution, and this is my optimal x star. This is because of this exact line search thing. Because in exact line search, we are again doing an internal second optimization that will always ensure that the alpha is chosen such that your grad f is equal to 0. Is this clear? Okay. Now recall the definition of the order of convergence of a sequence. The higher the value of beta, the slower is the convergence rate. This is true. If you recall the definition, it goes something like you have at some xk plus 1 minus my optimal value is as k tends to infinite. This particular thing will be equal to some constant times power beta. This is how we define the order of convergence, and this beta is my order of convergence. So if this beta value is higher, then will it converge faster or slower? It will converge faster, but the statement says it is slower, so this is false. This is also something we discussed some time back. So we have an unconstrained quadratic problem. Minimize f of x is this, where Q is a symmetric and a positive definite matrix. Let xk denote the current iterate. The Newton direction of this problem is given by. We just told that the Newton direction is something like minus del square F inverse times del F. But we didn't explicitly calculate the value of this. Maybe you can quickly calculate and tell me which of these is actually the current this particular value of pk. So all you have to do is calculate the gradient of f, and then you calculate the Laplace of it, and then do inverse, and then multiply it with the gradient, and that will give you the direction of pk. Just take the derivative, so this will be that, and then if you take second order derivative, it will just give me q. So I have to do is substitute this in the original equation. So pk will be minus q inverse times qxk minus p. This will be, first one will be minus xk plus q inverse p. This could be one way of deriving, but if you also recall, Newton step will converge in, like Newton method will converge in a single step for a quadratic problem. So all I have to do is just take xk plus 1 as xk plus pk, and I know it will converge in single step. So what is xk plus 1? This will be my x star. And what is my x star? We know that grad f should be equal to 0 for an optimal, to get an optimal solution. So all you have to do is take grad f, so that is qx star minus p equal to 0, which means x star equals to q inverse b. So you can substitute that back. So xk plus pk equals to x star, that is q inverse p. So pk is given by q inverse p minus xk. Whichever way you feel comfortable, like either way, this is the solution. This is clear. This we just discussed now. What is the number of iterations you have to do for Newton's to converge it to optimal solution? With just one iteration, it will converge, because again, all you have to check is the function quadratic. So there is another trick that we kind of often do in some of these problems. So for example, you're trying to solve a problem where you do not know the objective function directly. So what we do is, say you have some function, you don't have the function values, but let's say you calculated the objective function during multiple iterations. This is your x, say x0, or let's say these are some x values. I'll just put x here, and this is my objective function values. I don't know what the function is between these values, but I have calculated at some points of x, I know the values of x. And let's say I want to do minimization problem here. So what I can do is always fit a quadratic curve in this region only for these 3 points. Fit a quadratic curve, fit a curve of the form ax square plus bx plus c. Like you find these ABC values. Basically, you have 3 points, 3 function values, and you have 3 unknowns here. So you can solve 3 problems, like 3 unknowns, 3 equations, and you can get the values of these ABC. And once I fit this curve, then I can start at any point on this curve and then eventually find what the optimal value is. Like I have drawn it here as if this is the optimal, but it can be in some different form as well. So let me just draw a different case. So you can have the function value something like this, or something like this. When you fit the curve, it can be something like this. So you can find this will be my optimal point. So you fit a curve for these 3 points, and then you have a quadratic equation. Then you can use the Newton method to simply find the solution of this. So this will be my direct solution. This also we kind of do it sometimes. So there are other, like instead of doing this, you can always fit a linear function. But if you fit a linear function, then this might not converge fast. So if you fit a linear function, what is the optimal value? If I fit a linear function, then it goes something like this. Then this will be minimum, right? Because this is the minimum I can find for that particular functional form. This is something like the linear optimum. But if I fit a quadratic function, then this will be my quadratic optimum, right? Yes. Sorry, if the order increases, what will increase? Hmm. That we cannot say, right? We do not know what the actual ground truth is. That depends on the physics of the problem. Like if this particular function, like the original function relation itself is say quadratic, then the quadratic might be the accurate one. But if the original relation itself is linear, then using the quadratic will give you a wrong solution, right? So that depends on the problem. Okay, maybe this you can solve pretty fast now. So you have a function f of x is x square minus y square. Take any starting point and apply Newton's method. At which point does the Newton method converge? The answer is obvious, but it's better if you kind of solve it once so that you know how the method works. Like what is the minimum of this particular function? Yeah, like even without solving now, you know that Newton method will converge in single step, so you know where it will go to. Like this will be minimum only when both are zero. Like if okay, then I will be assuming that x comma y are greater than or equal to 2. Only if this is true, then this will kind of eventually go there. But otherwise, it can go to minus infinity. So, but let's try doing Newton method for this. What will happen? So if you try to do Newton method without this constraint, let's say x, y greater than or equal to 0 is not there. Both of them can belongs to R. So let's solve that particular thing. Let's say x comma y belongs to R. Then this y can keep on decreasing. X can like it can keep going to minus infinite or something. So there is no minimal for this. But like the optimal solution does not exist. The finite optimal solution does not exist for this problem. But let's say if you apply Newton method for this, how do I start? So first I calculate my grad f. Grad f is 2x 2y, and if I calculate my Laplace, that will be 2 0 0 2. So my direction p will be f inverse times grad f. So this will be minus. If I take the inverse, so this will be 1 by 4 2 0 0 2 times 2x 2y. This is minus x minus y. So if I put pk, then this will be minus xk and minus yk. Now xk plus 1 yk plus 1 is xkyk plus pk. So this will go to 0 0. Now once I reach 0 0, what will happen? At 0 0, my gradient of f will be 0. So p will become 0. Like at 0 0, pk equal to 0 0. This implies this gets stuck. So the Newton method is converging to this particular value 0, 0. But is it the true optimal? Like if you want to minimize this function, I can always choose say x equal to 0 and say y equal to 10 or something. Then this particular value will be less than that. So the minimum will be somewhere else. But still, if I use Newton method, then it is converging to this particular thing 0, 0. So again, it's the same thing that we discussed in week 1. We have to ensure that an optimal exists in the first place, and then you have to use some strategy to find that optimum. If it doesn't exist, then using some strategy might end you might end up in a different solution. Like you might end up at some point which might not even be a solution. That will be solution for your strategy, but not for the problem that you have chosen. That is something that you have to always be careful about. Okay. Now let's say we have these constraints, inequality constraints, g of x less than or equal to 0 be the feasible region. Assume g to be continuous. Which of the following can be used as a penalty function? So if I have to use that as a penalty function, what we have to do is I have f of x plus some constant times my penalty function. This is say my q of x comma c. So if that particular whatever function of this, if I choose my penalty function, it should be such that when I minimize this q, this penalty function should go to 0 and I should be minimizing f of x. Then I can consider that particular function to be p of x. So if let's say we'll do one by one, if we take the norm of g of x, then what happens is when norm of g of x equal to 0, then this particular constraint is satisfied. But then it is kind of a more stricter case. Like the original constraint says that g of x can actually be less than 0 also, but this constraint is kind of forcing it to be equal to 0. So you can use this, but then this will be more a stronger constraint, and you might actually miss out the points which are actually interior to the point. It's like this will only capture the points that are on the boundary of the physical region, but not the interior ones. So the constraint is not actually physically represented if you use this particular penalty function. Now let's say if I choose this minimum g of x comma 0, then what will happen is p of x will always be, as long as you're in the feasible region, this will be some negative quantity and this will keep reducing, and then you will not be able to find a minimum of, you'll not be able to find the minimum. So this will not represent the region. Like we have already seen, this particular quantity will represent the region, because if g of x is negative, then it will go to 0, which means p will be 0 and then I'm minimizing f of x. If it's outside the point, then g of x will be positive and then that will enter the penalty function, and that will ensure that like when I minimize this, then the algorithm will try to reduce the value of p of x to 0. So g of x will get reduced and this feasible region is represented. What about this function? Can I take something like this, g of x minus alpha square? So what this condition does is we are ensuring that g of x is equal to alpha. Like when we try to minimize this, so this is something that we often do when you have an equality constraint. Like we formulate it as h of x equal to 0, but then it will not always be equal to 0, but there is some finite tolerance that you can always have. So if not for the tolerance, let's say you have h of x equal to some particular constant alpha, this constraint will ensure that g of x equal to alpha. So essentially it becomes an equality constraint. The original one is an inequality, but then it becomes an equality. So this is also not the problem that we are searching for. So the only way out of these combinations is this. Yeah, if g of x is greater than or equal to 0, then you would be choosing this. Yes. So instead of this, you can also write this as, so you're saying something like this. No, but then the problem would be like you're finding minimum of this, and no, that wouldn't be true, right? So if you see, I want g of x to be negative. If g of x is negative, minimum of g of x and 0 will give me what? Will give me g of x, right? Then minus of g of x will be some positive quantity and that will enter the penalty function. I don't want g of x to enter penalty function when I'm in the feasible region. So it's like, this is my feasible region, g of x less than or equal to 0. Whenever I'm in this region, I need to have p of x equal to 0. Whenever I go outside the region, I need to get mod g of x somehow into that picture. It's like, okay, or To be more precise, let's say it should be greater than 0. I don't want my p of, first thing is I don't want my p of x, like the penalty function, to be negative. I always want it to be some positive quantity, and it should be 0 only inside the feasible region, and anywhere outside it should be some positive quantity for a minimization problem. If it is a maximization problem, then it would be reversed. Inside the feasible region it should be 0, and outside the feasible region it should be negative. Right? Yeah. Then the other ways that you can kind of see the problem here is when I put maximum of g of x comma 0, and then you would be okay. We will see that in the next week. We have some augmented Lagrange and other stuff in the next week. Then it will be clear. So now let's stop here. Okay. There are again some theoretical questions. So when you have the steep and gradient descent applied to a function with exact line search, then the rate of convergence is linear, quadratic, superlinear. Which of these about? We solved a problem just some time back. So we took a quadratic optimization problem, and then we found that when using steepest gradient descent with exact line search, we converged immediately to 0. So it will be quadratic only for the special case when you apply steepest descent with an exact line search. Have some questions? Okay. The last question I have: the rate of convergence of Newton's method is quadratic throughout the feasible region. Is it true or false? Yeah, it depends on the problem. It depends on the feasible region. It will be quadratic only near the solution, but otherwise it's not. So in general, it may not be quadratic always. Yeah. So these are the questions I have. To quickly summarize, we started out saying why we need optimization method, because we cannot search through all the points. So somehow we have to reduce the search space. And for that, we need to use extra information like about the functional form, like whether it is continuous or not, whether it is differentiable or not. Somehow we have to use that information, and that is where all the different methods of line search come in, wherein we exactly use the information of the continuity and as well as the differentiability. So we use this to determine, like if I am at a given point, I will decide whether to go in the positive direction or the negative direction depending on the gradient. And then I also need to come up with a way to choose the step size, how far I should go using the conditions that are here. Like you will ensure that you go only so far that your objective value keeps decreasing, and at the same time your gradient also keeps in the same direction, so that you don't have to go move back and forth. Those are my work conditions. And then we saw that how to choose the direction is one way is directly use a gradient. But if you just use the gradient, the rate of convergence might be slower. So we have to use a higher order information. So we started. Then comes the Newton's method, in which in addition to gradient, we also take the Hessian into account. That will tell us what the curvature is. So now we know that instead of going in a straight line, now we can exactly use the information of the curvature and take a bigger step. So this will ensure that you reach the solution much faster, but only only when you are close to the solution and the problem is quadratic in nature. And then we looked at something called exact line search, where the value of the step size, to determine the step size, we'll again perform another optimization. So in addition to the original optimization problem, now we have a sub optimization problem to choose the actual step size such that your f will be minimized for that particular step size. And when we use steepest gradient descent along with this particular function with exact line search, then it converges quadratically, but otherwise it is actually linear in general. Then finally, we looked at something called all the previous ones are for unconstrained optimization problems. Whenever we have a constraint, in order to use the previous methods, we have to convert it into a unconstrained problem. So we introduce a new function called a penalty function. The penalty function is such that it will be 0 inside the feasible region, and it will be some positive quantity outside for a minimization problem. So for that, all the inequality constraints, we'll pose this as something like the norm of them to be equal to 0. And for inequality constraints, we'll pose something like maximum 0 from g of x. This will ensure that the p of x will be made to 0 whenever I try to minimize q of x comma c. And then we discuss some of these problems. Yeah, these are the questions I have for this week. So if you have any other things that you want to discuss, we can discuss. I think we can end the session for this week. Thank you for joining.